In this video, we're going to take a deeper look at our Taylor polynomials. Now, in the previous video, we came up with a formula for the coefficients of this type of polynomial, and I'm going to remind you what that formula is, introduce some new terminology, and just maybe do a couple additional examples. So here's just our reminder. So if f of x is n times differentiable at x equals a, then I remember this notation that we introduced, the p sub n represents the nth degree Taylor polynomial that approximates f of x at this point is given by this formula. So it's the function value plus the first derivative value times the quantity x minus a plus the second derivative value at a over 2 factorial times x minus a squared plus f third derivative evaluated at a over 3 factorial times x minus a cubed plus dot dot dot. And then, yeah, we could go up as long as we have that nth derivative. We can find that nth derivative evaluated at a divided by n factorial and multiply by this quantity, right? So that's one way to write it. Let me just show you that this can be written in a nice sigma form. And to see where the sigma form comes from, notice here, it looks like the first derivative isn't divided by any factorial, but technically it is, because I can write 1 as 1 factorial, right? And then if you look at the denominator of just the function value, you're like, okay, well, what do I put there? Well, it turns out by definition, 0 factorial is also 1, right? So if you notice, if you look at the denominators, they form a nice sequence with the non-negative integers, starting at 0, and then 1, and then 2. They just happen to have the factorial function there as well. So I can use this, and I can give you the sigma form for our nth degree Taylor polynomial. So I like to use k for my sums. So k goes from, and I'm going to look at this denominator and say 0 up to n. So there. And then let's look at the pattern. Well, the pattern is you basically take that nth derivative, but here I need to specify the kth derivative. So it's the kth derivative evaluated at that specific point over k factorial. And what do we multiply by? We multiply by x minus a to the kth power, right? So that's the sigma form for our Taylor polynomials. Now, there was another mathematician, last name Maclaurin, that, I don't know, maybe he decided to steal some of Taylor's thunder, and basically when a, right, the special value of x here, when a is equal to 0, we refer to the Taylor polynomial as a Maclaurin polynomial. So let's write that down. So when a is equal to 0, we refer to this as a Maclaurin polynomial, right? And if you remember when we were kind of giving a sketch derivation of the coefficients, I made an assumption just to make it easier, just for a little bit, to see where everything comes from. We assume that our a was equal to 0, right? So Maclaurin is really just a special case of our Taylor polynomial, all right? Okay, so let's do a couple examples, see what this is like. Now, we did an example at a equals 0 in our previous video. Let's do a different sort of example now. At a different point. So let's say we're going to do some examples. And let's say our first one is this. Let's say we want to find p sub 4, right? So again, we're going to use this notation to represent the fourth degree Taylor polynomial that approximates whatever function at whatever point. So what is that function? I'll just say 4, let's say f of x. Let's take something like the square root of x, right? And then let's say at x equals 1. All right, so let's take a look at this. And notice again, I've chosen another function that is fairly easy to differentiate. So since we want the fourth degree Taylor polynomial, I'm going to go ahead and differentiate this function 4 times. So I'm going to write the original function, but this time with a fractional power. And then I'm going to go through and repeatedly differentiate. So our first derivative is 1/2 x to the negative 1/2. And I'm not going to rewrite this. I'm just going to keep it in this power function form and just keep differentiating. Our second derivative will be negative 1/4 x to the negative 3/2. Let's scroll down and give ourselves some more room here. And then our third derivative is, so what's that? Negative 1/4 times negative 3/2, sorry. So that's a positive 3/8 x to the negative 5/2. And we need one more. So I'll write my fourth derivative like that. And let's again bring down that power. So it's going to be negative 15 over 16 x to the negative 7/2, right? So good. So now we have all the derivatives that we need. Then we have to evaluate each of these derivatives at the point at which we want the approximation, or you could say the point of tangency, right? So f of 1, well, that's just 1. F prime of 1, that'll be 1/2. And then, I wrote double prime. So this is, let's get that off. There we go. All right, so then our second derivative evaluated at 1, that is negative 1/4. Our third derivative evaluated at 1, that is going to be 3/8. And then finally, our fourth derivative evaluated at 1 is negative 15 over 16. All right, so now we have a part of the coefficients, if you will. Remember, it's not just the derivatives, but we're going to have to divide by those factorials. So I'm going to write it out symbolically. In fact, let's do that so that we have lots of room. Let's do that right down here. So the fourth degree polynomial, and we can't call this one a Maclaurin because our point of tangency is 1. So our fourth degree polynomial, Taylor polynomial that approximates this function is, so it's going to be f of 1 plus f prime of 1. Now technically this is supposed to be over 1 factorial, but we don't write it. But we definitely have to write our factorials here now. Second derivative divided by 2 factorial times x minus 1 squared. And then we keep going. This would be our cubic term. Third derivative evaluated at 1 divided by 3 factorial times x minus 1 cubed. And then our last term, the fourth derivative, evaluated at 1 divided by 4 factorial times x minus 1 to the 4th power. All right, so let's go ahead and plug in and sort of simplify the coefficients, and that will be our polynomial. So f of 1, that was 1, or that is 1, and then plus, then we have 1/2 times the quantity x minus 1. And then now the second derivative evaluated at 1 is negative 1/4. So this coefficient is going to be negative, but then I also have to divide it by 2 factorial, which is 2. So I'm going to get negative 1/8. times a quantity x minus 1 squared. Now let's look at the third derivative. Third derivative evaluated at 1 is 3/8, and then that has to be divided by 3 factorial. Now 3 factorial is 6. So yeah, we could do a little bit of scratch work over here. So if we have, let's do it over here. So if we have 3/8 divided by 6, well, that's the same as 3/8 times 1/6. The 3 reduces the 6, and we have 1/16, right? So this is equal to 1/16. So that's my next coefficient. So plus 1/16 times the quantity x minus 1 to the third power. And now our fourth derivative divided by 4 factorial. 4 factorial is 24. So we do again some scratch work. So we got negative 1/16 times 1/24. Let's see how that reduces. Well, this one we can reduce it by 3, so that leaves a -5. And then this, when we reduce that by 3, it leaves an 8. So yeah, we're going to end up getting, what's that, -5/128. So let's write that down. So -5/128 times the quantity x minus 1 to the fourth power, right? And that's our fourth degree Taylor polynomial that approximates our square root function at x equals 1. Now, yes, the polynomial seems complicated, and we have all these quantities x minus 1 raised to these different powers. But in general, for Taylor polynomials, we don't even go ahead and expand them, right? This is another, actually, I wouldn't say it's a standard form, but it is a very useful form to have your polynomial in. So we're going to leave everything factored, and that would be our answer for this particular question. All right, let's look at a slightly different type of problem. So let's say we want to know where, so I'm going to ask this question. So does y equals e to the negative x and y equals x plus 2 intersect? So actually should be do, right? So do these two functions intersect? And if so, where? And so let's kind of think about it graphically first, right? Let's think about it graphically. And if I draw the graph of e to the negative x, so it has this sort of shape, right? That's y equals e to the negative x. And then if I draw the line y equals x plus 2, so e to the negative x has a y-intercept of 1. This graph has a y-intercept of 2, so it would just be above it. So like this, so like that, basically. So that's y equals x plus 2. And graphically, yeah, it looks like there is a point of intersection. So yeah, it looks like they do intersect. And the question is where? So how would we normally, find where the graph of two functions intersect, right? Well, if they're in the form y equals f of x, usually we would set this y value equal to this y value and solve, right? So if let me write that down. So if I wanted to find that x value where they intercept or intersected, I would set up e to the negative x is equal to x plus 2 and then I would somehow have to, do some algebra to isolate this. So let's say I moved everything to one side. Then I'd have e to the negative x minus 2 is equal to 0. So notice here what I've done. I've turned an intersection problem into a root or zero finding problem. So finding where these two functions intersect is algebraically equivalent to finding the roots of this function. But the problem with this function, now that I've written it this way, is that I don't have any nice way, no properties in algebra that I can use that could combine these two terms. And part of the problem is this on this side is algebraic. This on this side is transcendental, meaning it transcends algebra. So even though, yeah, they do have a point in common, I can't use any of my standard techniques to isolate the x. I just can't do it. You could try to mess around with logarithms and have at it. Take a few minutes, try to be clever and try to isolate this x. I guarantee you won't be able to do it, right? So then what do we do? Or then you might, grab your graphing calculator. Oh, my graphing calculator tells me what the point of intersection is. Well, it gives you an approximation, right? It gives you an approximation. It will never give you an exact form. It will give you some long decimal expansion. So it turns out that we can use the Taylor polynomial, right, and come up with an approximation of this point of intersection. So here's what we're going to do, and I'll show you graphically. I'm going to pick a convenient value of x at which I'm going to find, and I'll just use the first degree. So I'm just going to make it a nice linear equation. So I'm going to find the Taylor polynomial of degree 1 that approximates my e to the x at x equals 0. I like x equals 0 when I'm working with exponential functions, right? You can use different x values if you want. I'm just going to keep it nice and simple. So I'm going to find the tangent line, essentially my first degree Taylor polynomial, to the original function, right, my e to the negative x at x equals 0. And instead of looking at where the curve and the line intersect, I am going to find where the two lines intersect, and I'm going to use that as my approximation. So this is going to be my p sub 1 of x. And after I find what this equation is, I'm going to set it equal to this linear function and use this x value, whatever that comes out to be, let's say x sub 1, as my approximation to this mysterious red, right? So I'm basically going to use the green as an approximation for the red, right? So in order to do that, let's find our p sub 1. So since I'm just doing my first degree polynomial, I only need the function and the first derivative. So I'm going to restate the function. And then here is the function's first derivative, that is negative e to the negative x. Then I'm going to evaluate both of these at 0, right? Remember, I'm choosing 0 for my point of tangency. So y of 0, that one is definitely 1. And then dy dx evaluated at x equals 0, that's negative 1. So now let me write down the p sub 1, the Taylor polynomial of degree 1 that approximates my e to the negative x. It's my function value evaluated at 0 plus my derivative value evaluated at 0 times the quantity x minus 0. So let's plug in what we know. We have 1 there, we have plus negative 1 there, and then times an x. So we have a nice simple line. It is 1 minus x, right? So let me write that in over here. So now we found that this is 1 minus x. So if I am willing to live with a little bit of error, right? So I know I'm not going to get a perfectly accurate answer, what I can do now is find where my p sub 1 and y equals x plus 2 intersect, right? So let's set this up. Let's take our 1 minus x, set that equal to x plus 2, and I'm going to subtract x from both sides, subtract 1 from both sides, so I'll get negative 2x is equal to 1. So this tells me that x is equal to negative 1/2, right? And what I can say, so it's obviously not perfectly, it's not exactly equal to negative 1/2 where they intersect, but it's a good approximation. So I can say that y equals e to the negative x and y equals x plus 2 intersect. So they intersect at approximately, that's the key now, we're approximating, so at approximately x equals negative 1/2. And if I wanted a greater degree of accuracy, I could replace the original function with maybe a quadratic, right? Or what I could do, I could pick a value of x that was sort of closer. So instead of taking 0, which 0 is convenient because of how easily we can evaluate it, if we wanted something closer, maybe pick something like x equals negative 1/2. And then we will get closer and closer to that point. So there are different ways that you can improve approximations that are based on Taylor polynomials. One, you can increase the degree, but sometimes when you increase the degree, finding like solving equations with higher degree polynomials, then that poses yet another set of challenges, right? Which we often rise to. Or you could change the point at which the Taylor polynomial is constructed. In other words, where are we going to build it? Are we going to build it at x equals 0 or at some other values of x, right? So that kind of gives you, again, a couple other examples of ways of not only finding the Taylor polynomials, but how we can use them to solve other important problems, right? In the next video, I think I'm going to give you kind of a visual as to what these polynomials look like. I mean, my sketches are at best, okay, right? Those are my good days. But as we're kind of building to something a little bigger, I want to make sure that you have a good visual of what's going on. So I'll see you in the next video.